The second skill that we need when we are comparing molecules and the intermolecular forces that they will possess is we're going to need to be ready to compare polarity. We need to be able to identify if a molecule is polar or nonpolar to determine how it's going to behave around other molecules just like it. So we talked about this when we talked about molecular structure. I'm going to run through a refresher on how to determine molecular polarity for a molecule if you're just looking at the chemical formula or a 2D structure. So we're going to take, for an example, C2H2F2. And the first step, if you have just the chemical formula or if you have a 2D structure, is to start thinking about it in 3 dimensions. And so this might mean first drawing a 2D Lewis dot structure. For this one, I might do something like this. And then translate that into a 3D structure. And so for a carbon that has 4 things around it, it'll form a tetrahedral geometry. So I know I'm going to have this 109-degree bond angle between all the atoms surrounding it. So like this difference right here, this will be 109 degrees. And I can put in my atoms. Here we go. So now I have this 3D picture of my molecule. And I'm using wedges and dashes to show the dark wedge right here is showing that the fluorine's coming out of the plane of the paper, and the dashed wedge is going back into it to kind of give a little bit more information about how this looks in 3 dimensions in a way that's highly structured. All right, so then following that, we are going to use the electronegativity chart that we have to determine if any of these bonds are polar. And so looking at this, we have carbon-hydrogen bonds and we have carbon-fluorine bonds in our molecule. So I'm going to look at the difference in their electronegativities. And looking at the chart, I know that my carbon has an electronegativity of 2.5. And hydrogen has one of 2.1. And my fluorine has an electronegativity of 4.0. So I'll take the difference between those two numbers. I'll have 2.5 minus 2.1, that equals 0.4. For my carbon and fluorine, that's going to be 4.0 minus 2.5, which is going to be 1.5. So I'll use my benchmarks for polarity for a polar bond or a nonpolar bond. And remember, that is between 0 and 0.4, I have a nonpolar bond. And so that 0.4 falls in that region. And if I have something between 0.5 and 1.9, then I have a polar bond, and my 1.5 falls in that region. So I could say that my carbon-hydrogen bonds are nonpolar and my carbon-fluorine bonds are polar. All right, so I now know that I have some polar bonds, some nonpolar bonds. I have a 3D shape. Next is the kind of harder part, is to determine if the overall molecule is polar or nonpolar. And so usually if you have a polar bond, you have a polar molecule. There are a few exceptions to this. If all of the bonds are polar and there is symmetry around the central atom and no lone pairs, then you will have a nonpolar bond. It's like having a symmetrical, uneven sharing of electrons. Just kind of a mouthful there. So looking at this one, I have just 2 of these 4 bonds are polar. I'm going to represent that with a little dipole arrow along the bond. My fluorine is more electronegative, so I have my arrow pointing towards it. And then if I want to think about the overall polarity of this, I could see that I have 2 polar bonds and 2 nonpolar bonds. And so these aren't going to cancel out in this kind of, there isn't a symmetry to how uneven these bonds are sharing electrons. So I'm going to kind of think about the average of them, and I'm like, oh, well, you know, that's about in between these 2 fluorine would be the overall kind of dipole moment or direction that electrons are going to be more likely to be found in. So I can say that this is a polar molecule. And so that's going to be an important skill for determining how a molecule will interact with another one. There is this one kind of something that we'll use a lot more next week, which is a molecule can have a polar bond, but if it's a very large molecule that has lots of nonpolar bonds, just like a few polar bonds, then it will actually behave like a nonpolar molecule because the majority of the molecule and so much of it is nonpolar. And we'll introduce kind of like a benchmark to determine if that is the case, and we'll talk about that more as we talk about solubility. Let's look at an example continuing the one we did and compare these three molecules and decide which ones are polar and which ones are nonpolar. So they're written in 3 dimensions. So we're looking at them and we have to decide, all right, are there any polar bonds? And is the molecule overall polar? So these are all bonds that we've already just talked about in our example. So we know that carbon-hydrogen bonds are nonpolar. And we know that carbon-fluorine bonds are polar. And so I'm going to go through and add these little dipole arrows to represent that. So these fluorines are going to be polar, and also all of the ones on this. That first molecule has only carbon and hydrogen, so they're all nonpolar. So now if I want to go through and decide which of these are polar and which of these are nonpolar and kind of label them, I can go through and assess the kind of overall polarity based on the dipole moments. So in the first one, I have no polar bonds. And so if I have no polar bonds, I have a nonpolar molecule. It's kind of the easiest situation. So nonpolar for our first one. Our second one is the one we just talked about, as it was our example. And we determined that it was polar because it had an imbalance in polar and nonpolar bonds within the molecule. So polar. And our last one is one of our exceptions. It has polar bonds, but all of them are polar. There's no lone pairs on the central atom, carbon, and so they're all perfectly spaced away from one another, which means they're symmetrical. And so all of those polar bonds are actually going to lead to the symmetrical shape around the central carbon, and it won't behave as if there's an imbalance. So it is also nonpolar. All right, so of these, only one of them is a polar molecule, and it's the central one right here.